So thank you for being here. My name is Stephan Zuijdendorp. I'm from Process Sensing Technologies, a global company offering measurement solutions in the widest sense of the definitions. I picked out, of course, a hydrogen topic here today, measuring or controlling the safety and quality of electrolyzer operation. So I think everybody would recognize this, a simplification, of course, of a electrolyzer with a cell stack and a separation skid for both gases to be produced. And a lot of these things could go wrong, right? And you want to make sure it's dangerous material, hydrogen, especially in combination with the oxygen, of course. We all know the experiments probably from the school in the past, where we did nice explosions. So at the cell stack, a lot of things can happen. Seal and connection damage, stack compression can go wrong, contamination from outside, if the water is not pure anymore, maldistribution of electrolyte, catalyst activity losses, degradation of the membrane. Actually, a lot of these are related to each other. Maybe even design issues, although you want to prevent that, of course. So that could implicate hotspots, leaks, and especially crossover of hydrogen and oxygen. At the separation skid, there is a lot of material there, of course. The heat exchangers we just saw, valves, pumps, all kinds of sensors measuring the process and controlling it. Maybe level controls which are not stable, corrosion, hydraulic shortcuts, insufficient purges. Same kind of implications, especially the crossover of hydrogen and oxygen. So analysis, you could consider that be the last defense for safety. At the stack level, there are many things to monitor to basically prevent those dangerous situations, like the plate voltage, dish springs. You can use flow metering, of course, all kinds of temperatures. But a lot of these things are indirect determination of crossover of these gases. So at the separation skid, there are two main parameters, and you see that basically everywhere in the world, people doing this, where we have the oxygen to hydrogen, where you monitor the oxygen to be below the 4%. To prevent immediate danger. Then there are nominal levels and alarm levels considered, of course, the typical alarm levels, typical I say, so some people do it slightly different. 1 volume percent is already a warning, and 2 volume percent could be something to switch off your system. And the same counts for the other side, hydrogen to oxygen. Same kind of levels are being used. And this could be, or is, a direct determination of the gas crossover. So, therefore you need a reliable analysis technology, stable sensors, and you can choose between depleting sensors, have a low capex, higher opex, has advantages, disadvantages. Non-depleting, higher capex, and very low opex. There's not a lot of maintenance needed. Process conditions can be a challenge to measure. They're often saturated with water, and we talk about gas measurements, and everybody can understand a gas analyzer cannot handle liquid. That wouldn't be fair to ask for, right? So you need to prepare the sample for that. There will be fluctuating process and ambient temperatures. Due to the intermittency, a lot of electrolyzers are being switched off when there is no sun or wind, or both, and switched back on if it is there. So you need a sample system to condition the sampled gas. You need to do pressure reduction, usually cooling or heating even, filtration. You need functionality interlocks like liquid detection, that you do not flood equipment. You don't want to be flooded with water. So this is just an example of a high-end system be supplied to a customer, where you see both measurements at one panel. You need to consider hazardous area certification, obviously. Around the electrolyzer, there will be an area which is considered to be hazardous for explosions. So that needs to be specifically for hydrogen. It can be EXD or IS. Other certifications can be in place as well. User-friendly in the end. There's still a human factor. People need to be able to work with it and maintain it. Although this looks like a complicated system, there's not a lot of maintenance here. Then there is, of course, the SIL topic. SIL-capable analyzers will be important, obviously. Sample system SIL capability to basically integrate that into your electrolyzer safety system. Then there is will be a presence of purged nitrogen. We need to deal with that as well. So then we go to the next topic, basically. For the oxygen to hydrogen measurement, purged nitrogen in the hydrogen gas. Electrolyzers are purged with nitrogen at commissioning, after maintenance, when things are being opened up. Some people do this all the time, not doing maintenance all the time, but purging between operation for safety precaution. So the sampled gas will contain nitrogen and declines from 100% to 0%. The duration of that depends on the dead space in the unit and the amount of hydrogen produced. So you need a measurement which is not dependent on nitrogen, at least a minimal dependency, to be able to measure right from the start of operation in a correct way. So this might bring you back to school. This is just to describe how this nitrogen will be present in your system. So the first differential equation determines the nitrogen concentration over time. Is basically dependent on the nitrogen concentration in the system, right, and being replaced by hydrogen. If you solve that equation, you get this exponential power function. And that looks like this. In this period, the first period, of course, will be a constant flow of nitrogen. It's being purged. And then at the start, when the power is switched on, hydrogen starts to build up, oxygen starts to build up, and the nitrogen will be replaced according to that formula. The constant, again, depends on the size of your unit, how much dead space is there, how much hydrogen is being produced, which is, again, a function of the power, of course. But typically, a curve like this will exist. So if you want to measure that oxygen in hydrogen, you want a low or minimal dependency of nitrogen to prevent measurements like this, where you basically start at a negative value in the beginning. That's not very good because you might just skip on an alarm which occurs. So that's why we introduced the XPM 601 paramagnetic oxygen and hydrogen analyzer, specifically for this application. For our electrolyzer analyzer portfolio. It's a paramagnetic non-depleting sensor, so it's very stable. No use of sensors which are being consumed, so there will be a stable response over time. There is no dependency or negligible dependency for purged nitrogen, so that you have the highest accuracy right from the start. It's based on our compact EXD process analyzer platform. We have other versions of this analyzer as well for other measurements, also at the other side of the electrolyzer, with a fairly small footprint. SIL capable for integration into your SIS, in your SIS system. Low maintenance and easy operation and calibration. So as a summary, just to give you an overview of what we can offer as PST in many areas of the hydrogen world, let's say, for transportation, for purification only, electrolyzers, we have many options. Gas blending, natural gas blending with hydrogen, steel production, I don't think this is even that complete, but there is many more to choose from. So I would say come to our booth and explain your application and what your requirements are, what your goals are, and we will be happy to discuss, and we can both learn from each other. Thank you.